All right then, now we start getting to the business end of the paper now. Question 5. Now, a lot of people would just look at this and go, nah, not having a go. But here's the thing. There are clues, because I got a less than and a less than there. And I got to the power of 9 to the power of 19 there. Then I've got in between a -7 and a -3, and a -7 and a -7 there. Okay, so now we need to go to 4 and 7.5, which is less, which is greater. Well, when it comes to -7s, -3s, -7 is a smaller number than -3. When there's no minus, 9 is a smaller number than 19. So let's just have a look at the trend in how it goes. So I've got the wavelength. Now, you should know wavelengths are bigger when it comes to radio waves and then smaller when it comes to gamma. So hopefully, because these two are less than, right, and they belong on the ends of something, we could get a few marks. It's worth 3 marks in total. We could get a few marks just by increasing that wavelength. Decreasing the wavelength. So it goes from big to small. You can see that by the -11 there. So I need to figure out which of these is my smallest. Well, because that is a range from -7 to -3, because -3 is a bigger number than -7, and this one's only got -7s, therefore this must be a bigger range, look, because I've got -3 there. So that's why I've put that there. So infrared, 7.5 times 10 to the -7, 1 times 10 to the power -3. So it's that range. So this is the bigger end, this is the smaller end. And it makes sense, really, because I am decreasing. And now I can put my 7s in this slot. And then it goes -8, -7, -11, -8, -11. So see how it's kind of, you'd expect it to go -7, -8, -8, -11. Well, it goes backwards because it's decreasing. So that's why it's -7, -3 there. So hopefully that makes sense. This is not something you can really learn in 5 minutes. It's plenty of practice with numeracy. And then it comes to my frequency then. Well, frequency is going to increase now as I go from radio to gamma. That's why it's so dangerous. So I'm going to put my smallest number at the top and my biggest number at the bottom. And I think that is then when that's probably an easier one to do. So I got 10 to the power 9 there, 10 to the power 19, because there's a lot more zeros after it. And just when you thought you were done with standard form, they wanted to rearrange all this. Now, for 1 mark, I think it's probably a fair bit of work there. But if you know your standard form and you're confident with numbers, then again, this should be fairly easy. So what's it asking? So here's your region. Starts with radio up to gamma. Energy in joules in the incorrect order. Let's put it in the proper order. Now, energy is going to increase as you go up to gamma. So, again, we'd be dealing with minus figures. And -24. Sorry, I shouldn't say we're dealing with minus figures. We're dealing with minus standard form here. So, -24 is a smaller number than -14. So that means there's 24 zeros before this 2. And this means there's 14 zeros before this 2. So I should be able to pick out those again. So they're on the ends. And then we're just going to go from 24 to 22, 19 to 19, 17 to 14. And gradually gets, the numbers get less as you go down. I feel like I've spent a bit too long on that because it wasn't worth that much. This one is worth a lot more marks, so let's spend a bit more time on it. So describe how the national grid provides a reliable supply of electricity, as efficiently as possible. So the national grid is a series of, is a network of cables, and power stations. They're connected all together just in case the demand goes up. So I've said there, supply and demand is monitored, and when more energy is needed or more electricity is needed than the base load is pretty much the maximum energy or electricity a power station can output. then energy needs to be drawn from other power stations. So you could see it as if you didn't have enough electricity in your house and your neighbour had plenty, then you're going to tap his door and say, can I borrow some electricity? And he said, yeah, no problem. And that's pretty much what power stations do. And that's why they're all connected via the national grid. Power stations burn fuel to boil water into steam. So I'm mentioning now how they generate electricity. This steam then turns a turbine, which is connected to a generator, which generates electricity. Now, your step-up transformers increase the voltage to reduce the current, to transfer over cables, because transferring energy at high current will result in heat loss from the cables. So you lose a lot of energy, and they don't want to do that, so they convert it to really high voltages. Step-down transformers bring it back down to 230 volts, which we can use in the house. There's one thing I want to mention here is when we're dealing with electrical circuits, as voltage increases, current increases, and that's because of the equation, how the equation works. You've got VIR. So if you increase voltage, then and you keep resistance the same, then current is going to increase as well. Whereas when you've got, I think, PIV, notice now how I and V are together. So when you keep the power the same, or if you increase voltage, then current's got to come down. There's a way to prove that, but I'm not going to do it in this video. We can do that again. But just be aware that when you're dealing with the national grid, when voltage increases, current decreases, and when we're dealing with electric circuits, when voltage increases, the current also increases. So we got a nice graph here. Like, we all love a good graph, and these figures are ridiculous. Look, just be aware now. Gigawatts, terawatts, hours, kilometers. Okay, there's a right mixture going on here, but don't panic. Look, because we got these multipliers. So you've got your kilo, your mega, your giga, your tera. Just like kilobyte, is it? Yeah, in computer terms, a megabyte, a gigabyte, a terabyte. Or a gigablob, as I say. I got an 8 gigablob camera on my phone. Right, so converting these, what does that mean? Gigawatts is 1 times 10 to the power 9, so that's 6,3, and then 9 zeros after that. All right? Your terawatts is going to be 12 zeros after that. Your kilo is less again, and you can always check. Let's have a look at the question. Right. Use the information above an equation from page 2 to calculate the efficiency of the national grid system at maximum demand. So, useful over total. You can get that from here as well. Look, efficiency. Where are you? There we are. Energy useful over total times by 100. Now, this should be an easy 3 marks so long as you're good at converting. And there's my Be Smart Mate, Stop Being Dumb reference again. So if it's big to small, you multiply. If it's small to big, you divide by 1,000. So let's have a look here. What we got? We got, what's your total here? Let's have a look. Where's your total? Well, it says there, maximum band. I didn't want to do that. I picked the wrong one there. Maximum band, 63 gigawatts. Whereas my energy losses is this one, look. So 1422 is my energy lost. So what's my useful energy? Well, it's going to be this one minus this one. But hang on, I got 63 gigawatts minus 1420 megawatts. So I need to convert one of them. I either need to put megawatts up to gigawatts, or I need to bring gigawatts down to megawatts. And the way I've done it, I've taken a gigawatt to a megawatt, because I'm going from big to small, so I multiply by 1,000. So 63 gigawatts is the same as 63,000 megawatts. Now I've got my total. I can minus my wasted, and that's going to give me 61,580. That's my useful energy now. And now I can use my equation, total over useful, times by 100. It's 98% efficient. That's really good. That's a good efficiency for 3 marks there. I should have left that out because I might need it. What have I done with that? Oh, let's just hope when we come to that. Is it there? No. Yeah, there it was. Oh, no. Wrong one. Let's just hope we don't need that. Use an equation. Yeah, I'm going to need it, aren't I? To calculate the annual mean power used in gigawatts. Now, rather than me trailing through, you're just going to have to trust me on this one now that I'm getting these figures from... No, I'm going to have to show you. I'm going to have to show you. Where is it? Where's my last one? I'm going to press pause a minute and find it. So I've just dug this sheet out because you are going to need it. It's asking here, so let me read the question. Use equation, power equals energy over time. To calculate the annual mean power used in gigawatts. Now, you've got to put it in gigawatts. So they've given me my time. So my time's fine. It's my energy that I don't know. So let's go back. Oh, look. So annual mean electrical energy used in the UK 360 terawatt hours. So it's a terawatt hour because it's very similar to the kilowatt hours that we use. And it's essentially the same equation. These are interchangeable. So I need to get 360 terawatt hours into gigawatt hours. And I do that by times in 1,000 because if we look on that front sheet, then a terawatt, just below that is a gigawatt, and there's a difference of 3. So that's 1,000. 3 zeros is 1,000. So I'm going to times that by 1,000. I got my energy is now 360,000 gigawatts. And then I'm going to put that over that, and I get 41 gigawatts. Not a bad equation there for 3 marks, because they give you it anyway. And I believe this is the last question then, which takes a bit of work for 2 marks. So it said, and it's just working out what's going on. At maximum demand, there is a spare capacity of 16.9 gigawatts. Well, I've done my output capacity minus the 63 there for maximum demand, and that does come out to be right. So if you take 79.9 minus 63, you're going to get 16.9. If you're wondering where I got those figures, let me show you. Because it says there, your maximum demand is 63 gigawatts, but its output capacity, the very peak of what it can produce, is 79.9. So the maximum demand is always less than what it can output. And that's what that question is saying there. A maximum demand, there is a spare capacity of 16.9, and I've calculated that right. Maximum demand is equivalent to 85% of total capacity. Well, my total capacity is 79.9. Now, when I find 1%, so I'm going to find 1% of each of these. So 85% of 79.9. Let me find 1% of 79.9 is 0.799. Now, let's find 85 of those, and that comes out to 67%, which is wrong, because it reckoned there it was 85% of total capacity. But that is actually 67%. My next one then is the difference in minimum demand between summer and winter is approximately 10,000. So look at my graphs, minimum demand, there we are, I've got it there, minimum. This is my summer line, this is my winter line, I believe, yeah. So summer, winter, and this is, yeah, about 2 squares, and each square is worth 5,000. So that is being ticked. The times of peak demand in summer and winter are exactly the same. No, because in the winter it's around about 6 o'clock, and in the summer it's around about 5 o'clock. So that's incorrect. And then the last one, difference in maximum demand between summer and winter is 150,000. Was it? Not 15,000. So that needs to be 3 complete squares. Well, you can see there's not. So this is the maximum in a winter. There's 2. Let's have a look. So that would be, actually I've got to take it back here. So that would be 55. Yeah. So, and then the peak demand there, I think, is around about, but it's not, it's not between 15, is it? You can see that. So that was around about 43. So 55 minus 43 is not 15. So that's why. And that's the end of the paper.